Section 1.2, example 1.7, evaluating an integral using the definition. See the definition of the definite integral to evaluate the function from 0 to 2 of x squared dx. Use a right endpoint approximation to to generalize a Riemann sum. Okay. All right, so what we're going to do is well, let's start with the definition of our right endpoint approximation. So that's our R sub n or f of x1. Remember, we're starting with the right endpoint, so f of x1 delta x plus f of x2 times delta x plus, we're adding all of those together, and f of xn delta x. I don't know exactly where to start from here, but kind of generalizing from what we did in the past, we started out with finding out what our delta x is. So we could start with that. So our delta x is equal to b minus a. So in this case, we're evaluating from 0 to 2. So this is going to be 2 minus 0. And let's see, do we see n anywhere? So use the definition of definite intervals to evaluate this function. All right, I don't see anything. So I'm going to assume that n is just some general number, or n might be infinity. So instead of, let's pretend we're integrating this right here. Instead of breaking up into like a couple of pieces, we're breaking this up into an infinite amount of pieces. That would actually make a lot of sense because we're looking at smaller rectangles to go off of. All right, so we have that. What is next? All right, so the next thing we did is we started off, like when we plug this in here, we start off with a, and then we slowly start adding, oh, we didn't even finish this part. That's just 2 over n. So what we did in the past, we started off with b, and we started adding in however big our delta x was. So what we're doing here is, let's see, Rn is equal to f of, in this case, we're starting off with 0. So we have 0 plus, we're starting off with x1. So we're moving our delta x over. So 0 plus 2 over n. And then delta x, which is our 2 over n here. And the next value, f of 0 plus 2 over n times, this was times 1. Let's fix that part. Times 1. We're multiplying that by 2 here, so multiplying by that 2 over n. And we keep doing that until we get to n. So plus f of 0 plus 2 over n times n. That's what we're ending up with. And still multiplying that 2 over n. All right. Kind of not too fond of this notation. Also, what we need to add in here is the limit as n approaches infinity. Because n isn't just n, right? We have an infinite amount of boxes that we're creating, or rectangles that we're creating. So the limit as n approaches infinity. All right, this kind of looks nice. Still not too crazy about it. But again, we'll look at the limit as n approaches infinity. Let's factor out that 2 over n. So 2 over n was being multiplied to all of those. Here, what we have is f of 2 over n times 1 plus f of 2 over n times 2. And we keep going. f of 2 over n times n. Let's see. I'm liking it, but let's try to, what was the function we were looking at? X squared. So let's evaluate that function at those points, see if it makes a little bit more sense, see if we could apply some of the knowledge that we've learned in the past. And goes from infinity to over n. And here we're looking at 2 over n times 1 squared plus 2 over n times 2 squared plus 2 over n times n squared. All right, I'm starting to see something here. What I really want to do is, so notice that we have a 2 over n for all of the terms there. So we could actually factor that part out. So let me show you how to do that. So within here, we're factoring out the 2 over n squared. And then what we're left with is that 1 squared plus 2 squared plus 3 squared, all the way up to n squared. Oh, well, that just looks like one of our summations. We actually have a formula for that one. So let's clean this up and add that function in, or that summation in. The limit as n approaches infinity, infinity here. We factored this out. So 2 squared is 4 times another 2 is 8. 8 over n squared, n cubed. And we're multiplying all of that with the sum as I goes from 1 to n of I squared. And we have a formula for that one. So let's add that in. Limit as n approaches infinity. 8 over n cubed. And in the past, we've said that the sum as I goes from 1 to n of I squared, that's n times n plus 1 times 2n plus 1 divided by 6. So we're going to apply that right here. So we're just going all the way up to n. So we have n times n plus 1 times 2n plus 1. And we're dividing that by 6. I see things that are factoring out already. So here that simplifies to 4, that simplifies to 3. We factor out one of the n's there. Leaves us with 2 here. Let's rewrite it, clean it up a little bit. So we have 4 times n plus 1, 2n plus 1 over 3n squared. All right, what I want to do is simplify, because if we try to plug infinity in, we're going to end up with infinity over infinity. There we go. Infinity over infinity, which I know we might be able to simplify things out a little bit better. So let's give it a shot. So the limit as n approaches infinity of, expanding the numerator, we have 4 times 2n squared. So 2 plus 3n plus 1 all over 3n squared. And let's simplify them. Let's separate them into different fractions so we could divide some of the the values out. So we have 4 times 2 is 8. 8n squared over 3n squared plus 4, 8, 12. 12n over 3n squared. And lastly, 4 over 3n squared. Things simplify here. Things simplify here. 12 goes into 3 4 times. And nothing simplifies there. Let's see what we're left with. So the limit as n approaches infinity of 8 over 3 plus 4 over n plus 4 over 3n squared. All right. Now, as n approaches infinity, we're left with 8 over 3 plus that 4 over infinity, which that would just simplify to 0. And 4 over 3n squared, or 4 over 3 times infinity squared, which again, that would also go to 0. Larger denominator is not going to be a value. Right. So we're left with just 8 over 3. Perfect. And there we go. If you have any questions, please feel free to ask. Otherwise, bye.